Good morning everyone, and thank you for coming to this workshop. We'll be talking about how to scale models, and we'll be talking about it in a lower level. Like, we are not using any large frameworks. We are trying to understand how the operations in our neural networks are distributed when we scale, and how we think about communication versus computation when we scale our models to multiple devices. So to get started, you can go to this URL, mintext.readthedocs.io. The tutorial will be on Google Colab, and you'll find all the Jupyter notebooks that you need on this website. I'll put this up for a while so that everyone has opened the website, and then we can get started. So you'll see there's 4 tutorials. The 4th one is just sort of a preview of what's next. It's not ideal. Oh, okay, we are back. So you can go ahead and open the first tutorial, parallelization basics, and then you'll see there's a link to open it in Colab on top of the tutorial. I don't know how visible my cursor is, but it's right here. If you go ahead, click that link, it will take you to Google Colab, and the next thing you would want to do is you'll go to the runtime here in the Colab menu, and then you'd want to change your runtime type, and you'll use the V28 TPU runtime. So to expand upon a bit on the 2-8 means V2 is just the generation of TPUs that we are using. And 8 just means we'll have access to 8 TPUs of 8 GB each, so we'll have access to 64 GB in memory, or in terms of, like, you can think of as CUDA memory. Yeah. So once you have switched your runtime, save it, and then we can get started. And if you have questions about the setup, feel free to call me over. Yeah, I am happy to come by. Okay, so everybody good? On the tutorial, we have the V28 setup. Okay. So in this one, I'll be covering the basics of parallelization. So we'll talk about how matrices, which are the fundamental data structure that we use in machine learning, our data is represented as matrices, our models are represented as matrices, our gradients are represented as matrices. So we'll talk about how matrices are distributed across devices, and then when we perform operations on these matrices, particularly matrix multiplication operation, which is the main thing that we do when we do our forward pass or our backward pass, how to perform these operations when your matrices are distributed across devices. Okay, and for the tutorial we'll be using JAX, and the reason we are using JAX, well, the main reason is because we have access to 8 TPUs, so we can do distributed training for free. For Colab, you can usually use this runtime, the V28 runtime, about 3 hours every day. But the other reason is there's already great resources available if you want to learn about this in PyTorch. And I don't have access to 8 GPUs to grant each of you, so we'll be using JAX and TPUs. The other nice thing about JAX is, at least as a beginner, you can abstract away some of the underlying complexities that come with distributed training to get sort of the core concepts, and then once you have those, you can build upon those and get deeper into distributed learning. Okay, so we already did this. We set up our runtime. So let's go ahead, import the libraries that we'll need for the purposes of this tutorial. And we can check our device count. So we should have access to 8 devices, which are basically 8 TPUs with 8 GB memory each. The other nice thing I would say, if you want to run this locally, say if you run out of how much TPU access you have for the day, on Colab for free, you can have like 2 to 3 hours of access. You can simulate having 8 devices using this flag. So XLA is the compiler that JAX uses. So you can simulate that your CPU to have 8 devices, just like 8 different threads on your CPU will act to JAX as if there are 8 different devices. Okay, so now that you have run this, you should see something like this. You have available devices, TPU, device ID1, ID0, 1, 2, and so on. Okay, so let's go ahead and get started. The first thing we'll need to do is create a mesh of our devices. So what's a mesh? So mesh is a representation of how our devices are arranged in a matrix form. So like the corresponding to the data and the weights, we'll have equivalent sort of matrix in terms of our devices that will spread our data on. So let's say we pick 4 devices, we make a mesh which is 2 by 2, and this looks something like this. So we'll have, for our mesh itself, we have our mesh axes X and Y. Here it's illustrated like what we'll think of as X-axis is X, Y is Y. So this is our mesh. It is represented as a matrix. And next we'll start looking at how we can divide our data onto this mesh. So mesh is just a matrix arrangement of devices. Partition spec is essentially like how to partition your data or your array across devices. And JAX divide put is sort of similar to, if you're familiar with PyTorch, to CUDA is the same thing. So let's start with a matrix. Let's start with a matrix of ones, 8192 times 8192. And we'll define our partition spec. So we have X and Y. These correspond to the mesh axes. And we'll define a sharding spec. So what sharding specs mean is, given your data, how do you want to split it on your device mesh? So once I call jax.devicePut on my data with the shardings that I have defined, so the 2 by 2 mesh sharding, so our matrix now is broken up into these 4 parts or shards, and each part is assigned to a different device. Let's inspect our sharded matrix. So we started with a matrix of size 8192 times 8192, and now each device, each TPU has 1/4 of our matrix. So the first one has on the x-axis 0 to 4096, on the y-axis 0 to 4096. So this is like the top left column. The second TPU has on the x-axis the same, but the other half of the y-axis. So again, this is the bottom quarter, and then so on. So we have split up our matrix on 4 different devices. So this is not that important. The reason we do distributed learning or parallelization is to have matrix multiplication operations run faster, but we can also see like how fast element-wise operations run. And the thing about JAX is the compiler is pretty good. So it does a lot of optimizations under the hood for you. As you can see, like when we are doing the same element-wise operation on multiple devices, it runs faster. So I'll pause here. Like questions? Yes.
Yeah. So my question here is like, when you put the matrix into the shards,
Right.
Are you making a copy essentially?
It depends on how you do it, but you are not, like, you will make a copy when you're operating on them. Yes.
Okay.
Yeah.
So if I do like one sharded operation and then one unsharded operation,
It would not be ideal.
Yeah.
Yes.
And it wouldn't end up being like you do one and the other.
It might even end up being logically inconsistent, because like if you think about it, for example, for matrix multiplication, you need the whole row. And if you do it on shards, assuming that you have access to the full matrix, it might end up being the wrong thing that you get. So we'll get to that in a second. Yeah. So yeah, so the initialization in JAX is lazy. Like when you initialize your sharding spec and you say that this would be the assigned sharding spec for a matrix, it doesn't automatically get allocated memory, but when you do device put, then it gets allocated memory. Okay, so now we have two axes to think about. We have our data axes. So in this case, I've taken a matrix, two-dimensional matrix, 8192 times 8192, but we also have our mesh axes. So in this case, we have a 2x2 device mesh. You don't have to have the same sort of dimensions on both the data and the mesh axis, but for simple, like for making it simple, we'll have the same mesh axis and device axis, mesh axis and data axis dimensions. So I'm just redefining what we had earlier, a small 2x2 mesh. Now, what we can do is we can shard the first dimension. So this just tells how to place the matrix on our device axes. So the first dimension is being sharded along x, the second is being sharded along y. So this is what we saw earlier, and you'll see if I visualize it, it is the same what I showed here earlier, the same sort of breakdown. But we could also switch up our shardings. Yeah, I think this should be this way. So instead of sharding the first axis of the data on the first axis of the mesh, we could have the first axis of the data sharded on the second axis of the mesh. So this would look different. You'll see that the shards are now arranged differently on the mesh axes. The first one is the same, but the second one is now on TPU2. And we can also have some dimensions sharded. So some dimensions are split on different devices from our data, but other dimensions aren't. They're replicated. And we'll see how this comes into play when we talk about data parallel training, where we have our data sharded on different GPUs, TPUs, but our model is replicated on each TPU. So every device will have a full copy of our model. So for our simple example, if you want to do something like that, you'll see that the first dimension, the rows are sharded on the x-axis of the mesh, but the y, the columns of the matrix are replicated on both. And we can do the same thing. We can shard our columns and keep the rows on both devices. So for a 2D matrix, there's like combinatorial number of shardings we can do for a 2D matrix sharded on a 2D mesh, and I've visualized them here. These visualizations are from this great book called How to Scale Your Model, and I have the references in the notebook itself. So now I have talked about how you could split your data on different devices. Now, how do you choose how to split your data? And this will become clear as we talk more about how different parallelisms are implemented. And we'll also talk about what this means when you perform matrix to matrix operations, like how much is the cost of moving data around when you are doing your operations. So I'll pause here for a second. Questions about sharding, device, how the devices are arranged, how the data is arranged, how the data is arranged, mapped from the original matrix to the devices. Sure.
If you have a non-square matrix or non-square device mesh, does JAX sort of handle that neatly, or are there any special considerations there?
It can handle it neatly. It depends sort of what the mapping is. But for example, so JAX has 3 levels of parallelism that you can implement. One is almost automatic, where you can think of it as like automatic type inference in programming language. Like it figures out by itself what the sharding should be based on the operations that are defined. The second one you can think of as almost like type hints, where you give it, oh, this is how you should shard it, and then it will try its best to shard it that way. But the third is like fully manual, where you define the exact shardings. So for the first two, the auto and the hint type sharding, if you tell it, oh, you should shard an 8-dimensional matrix on dimension with like 8 on one matrix to like 3 on the mesh device axis, it will just not do it. It will just replicate it or figure out what's the best way. But if you do it in manual setting where you are manually defining everything, it will just throw an error.
So there isn't like a scenario where, like these are obviously like perfect, partitions of the data.
Right.
Is there a scenario where basically you have some residual amount of the data that, or like remaining amount of the data that needs to be like mapped to the device, for example, or yeah, like it just doesn't really handle that, like it'll throw an error.
So for example, say if you're training on a batch and the last batch has less than like whatever batch size you had. So you have two options, right? You could pad it or you could drop it. So the same way it has two options. It can either pad it or drop it. Usually it will drop it. And if you want to make sure that the operations are run correctly, you need to handle that part of the shard. Okay, so let's move on. We have split our data on multiple devices now. So each device has access to only a part of our data. This could be the training data that we are training on. This could be our model parameters. This could be our gradients. Now, when we want to go ahead and perform operations on them, now we need to take into consideration how it's split. So in machine learning and deep learning, usually the two most common types of operations are element-wise operations. So this could be something like ReLU, where you are operating on a single data point in your matrix. Or there are matrix multiplication operations like dot products or matrix products. So for this, the first one, we don't really have to worry about how the data is sharded. We can perform individual operations on each element of our data. But for the matrix multiplication, now we need to think about how the data is sharded across devices. And the nice thing about matrix multiplies is you can think of them in terms of block matrix multiplies. So for example, say you have this 4x4 matrix. You can think of each of these as small matrices of like 2x2 sizes. And now when you perform the matrix multiplication with a similar like block matrix, now these operations are essentially just operations on these small blocks. So the nice thing about this block nature of matrix multiplication is you can perform certain operations on the data shard that you have access to on your device. And once you have performed that operation, you can perform some sort of a collective operation where you bring together information from across devices to make the output logically consistent. So for example, like a simplified example, but if this was on our first device, this was on our first device, we can do this entire operation on the first device without having to worry about the rest of the data. And then similarly, if this was on our second device and this was, say, third device, then we'll first need to bring this from the third to the second, perform this operation, and then we'll continue. So this is where collectives come in. You're trying to collect information that has been distributed across devices. So there are 4 cases that can happen for matrix multiplies. So the first case is your contracting dimension. So in matrix multiply, say if you have an m by n times matrix multiplied by an n times k times matrix, so n is your contracting dimension, because once you do the matrix multiply, n goes away, you just have an m times k. So if there is no sharded contracting dimension, so the inner dimension on which the matrix is being multiplied, it has not been sharded. So this is great. So if we have this situation, we don't even need to worry about any collectives, because each part of our matrix can be operated on that particular device without worrying about the rest of the parts. And I'll illustrate this with an example. So I have created two small 4x4 times matrices, and then I have sharded them in a way that the first dimension of A is sharded along axis X. The second dimension of B is sharded along axis Y. So here is the mathematical representation. First dimension along X, second dimension along Y, and the contracting dimension has no sharding. So it's replicated on all devices. So let's visualize what this will look like. No, I didn't run the previous one. Okay, so let's see what this looks like. So think of these as some rows of your matrix and these as some other rows, and they are split up into two shards, and these are some columns of your matrix and these are some other columns, and they are split up into two shards. So when you do row matrix multiplication, you multiply this row by this column. Okay, maybe I'm not. I'm not sure why it's 0, 2 here, but essentially this should be the same shard devices as this one, and then that way you'll have this row of matrix A being multiplied by this row of matrix B, and since they are on the same devices, you can do that that operation on those devices without having to move data around. So afterwards, after the multiplication, now each device should have like a complete shard of the entire matrix, entire resultant matrix, and we can verify this by here I've just performed the full matrix multiplication and the sharded matrix multiplication and checked if the values are the same. And I'll need to check why this is this way. I think there must be a bug somewhere. So this is kind of a drawback of JAX's automatic compiler. Like, it solved some of these shardings from me behind the scenes. If I had done it manually, it would have thrown an error. Sorry, yeah, go ahead.
Which should it be?
So the way it should be is like these, since these rows of A are on a certain device, and the same corresponding columns of B should be on that device. So that way, when we are multiplying this sort of row with this column,
So it means 0.
yeah,
I think it is just the TPU number maybe because the previous
yeah, it is the ID. I don't know if it's the same. Yeah, that could be it.
Yeah.
But is this part clear? Like, because we are doing block matrix multiplies, right? So if you think about it, like if all the corresponding blocks for this operation are on the same device, we don't need to move any data around. All of this 4 operations can be done on one device. And any of these shardings, for example, where like A and B are fully replicated on both meshes, or the first outermost dimension of A is sharded, or the outermost dimension of B is sharded, or both outermost dimensions are sharded. All 4 of these operations don't involve you moving data to perform the operation, because we can operate on the individual shards and they are logically consistent. You get just a 1/4 of the full matrix multiplication now. So this is the easy case. Now we move on to some harder cases. So the second case is where one of your matrix multiplications, in this case A, the example that I'm showing, has the innermost dimension sharded. So this dimension, for example, in A, these are the columns. They are split up across devices, but for B, the rows are not split up. So now if you go back and think about it, or I have a visualization here, great. So again, I'm creating 2 4x4 matrices. Now, you have your columns of your A sharded, but the rows aren't sharded. So when you want to do a matrix multiply, sorry, I'm just right. So when you do your matrix multiply, you'll need this whole row of A, right? You need this, like it's easier to highlight for A, but you'll need this row. But now on any device, you only have access to half of the row. So when you try to do the multiplication, each shard will not contain the correct information for the matrix. Plus the dimensions will just not match up even. So you can't do the block style matrix multiplication anymore. So what we need to do is we need to perform some sort of an operation to gather information from across the devices into each device. And this operation is called an all gather. So here's a 1D example, like you have a one-dimensional array, it's split up on 4 different devices. So what we want to do is we move each part of our array onto all of the devices. So this is called an all gather. Here's a visual example. So now we have the entire array is 3952, but each device has only a part of our array. So the first one has 3, the second one has 9, the third one has 5, the fourth one has 2. And what we want is at the end of all gathered, each device should have the full array. So in JAX we can use, this is part of the manual parallelism. You can use all gathered to collect the shards from each of the devices and move them to one device. This is just being visualized here. First you have 3952 on different devices, and then after the all gather you have the same array on all the devices. I'll go back to the matrix multiply in a second, but the way we do all gathers is first you have all these shards of the array across different devices, and then you move them in a bidirectional manner. So you'll move each shard to both of its neighbors, and then say you had n devices, so in n by 2 jumps from like device to device, you'll have the fully replicated array on all the devices. So I'll pause here for a second, like with all gather if there are questions. Okay, so let's go back. Now for our matrix multiply, we had the second matrix was fully replicated, the first one was sharded on the inner dimension. So we first call an all gather. We gather the shards on this dimension, and now we have the full matrix. And once we have gathered, now we can perform the matrix multiplies on each device, because each device has a full copy of the matrix. So this is just the code for doing that. There was a typo. So yeah, this is the code for doing that. We have our input, the first input matrix sharded on the inner dimension. The second input matrix is not sharded on any dimension. The output matrix is again replicated, sharded, not sharded on any dimension. We first do an all gather of the first matrix, and then we perform the multiply, and we can verify that it's correct. Okay, I'll continue for now in the interest of time, but maybe after tutorial 1 I can take a pause and take questions about the collectives. Okay, so now an even more complicated case. Now we have both matrices that are sharded on the contracting dimension. So this is okay, because now if we do the multiplication, the inner multiplication, it's fine, the dimensions match up, because each shard has the same number of columns of A and number of rows of B. But after we have done the multiplication, we don't have the full row times column. We only have part of the row times part of the column, right, on each shard. So this is what's shown here. Like when we do the local matrix multiply on each device, it's unsharded, unreduced along the axis that was sharded. So what that means is, say for example, I think I have a visual example here. So if you had these rows are on TPU01, and these columns, these columns of A are on TPU01, these rows are of B are on TPU01. So when you do the individual multiplications, you are getting only these many columns times these many rows. You are not getting the full output of the matrix multiply on each device. Does that make sense? Yeah. So what you want to do is now somehow collect the information from the different shards and have each shard the full output of the matrix multiply. So for this we use something called all reduce. And reduction functions in CS and machine learning in general are functions that take multiple pieces of data and combine them together in some way. So sum is a reduction function, mean, minimum, max, these are reduction functions. So now, for example, what we need to do is each shard has 1/4 of the matrix multiplication result. We want to collect all of these and add them together to get the full matrix multiply. And this is called an all reduce. So in JAX, since the sum is the most common all reduce that's used in machine learning, it provides an all reduce sum as a built-in function. So what's happening here? Let me walk you through it. So each part has 1/4 of the final result. So the final result should be 3 plus 5 plus 5 plus 9, 22. So each part has 1/4 of the output. And what we want is all the parts should have all the outputs, and then we'll add them together. So this is what's happening here. So we add up all the outputs from the 4 devices on this dimension, same for this, this, and this. So we get the actual final array, 22, 20, 12, 17 on all of the devices. So this is just showing the operation that was shown in the image. This is the full example of the matrix multiply, and this is just showing what I just walked you through. Now in all reduce, if you think about how many operations are being done, first you are moving each piece of data across the device axis, and then you are adding them up. So the all reduce operation can be broken down into 2 different operations. So one of them is all gather that we saw earlier, where we distribute each shard on each device, so we have a fully replicated array on each device. The second one is called a reduce scatter. So a reduce scatter is whatever dimensions are sharded along, say, one axis, we reduce them, but then we don't replicate them across all the devices, all the dimensions. So we can break down our all reduce as a reduce scatter followed by an all gather. And with this breakdown, you'll see that all reduce essentially takes twice as much time as an all gather, because this is the same amount of data that needs to be moved along this axis, and this is the same amount of data that is moved along the other axis. So it takes twice as much time to do an all reduce than to do an all gather. So if you had that scenario where both matrices are sharded along the contracting dimension, in order to do the full matrix multiplication, you need twice as much time as if only one of the matrices were sharded on the contracting dimension. Okay. And the last scenario is if we want to do the case where both matrices have the outside mesh dimension sharded. So sorry, outside dimension sharded. So we cannot do this operation. We cannot have the same sharding on two different data dimensions. This does not make any logical sense. So what we'll have to do is we'll have to do an all gather on one of the matrices first, followed by a multiply. It could be either matrix. So it could be either we all gather one of the dimensions of A, multiply it with B, or we do all gather on one of the dimensions of B, multiply it with A. So what this will look like is if you first gathered A and then multiplied with B, the output you will have is sharded on the second axis. But if you first gathered B, multiplied it on with A, it will be sharded on the first axis. So this case, there's no really new collective that is being used. It's just we are doing all gather twice. First on one axis of the one of the matrices, and then for the response, for the output, we can do it on the other, or we could leave it sharded depending on what we have in our model. And another collective that I'll talk about here, but it will not be used in any of the tutorials that follow, is all-to-all. So all-to-all you can think of as almost like transposing your sharding. So you are transposing your shard dimension and the data dimension. So first you had in your data this dimension was like on device 0. Now you'll have this dimension on sharded along the devices, and this dimension which was sharded earlier now is all on one device. So JAX also supports all-to-all. So we'll be talking about data parallelism, FSDP, and tensor parallelism today. All-to-all is not used in those, but there are other sorts of parallelism such as expert parallelism that all-to-all is used. Okay, so this is what I was talking about earlier. Like JAX has 3 types of sort of level of control that you can have on your shardings. So one is auto, where you don't define the sharding, you don't define what collective will need to be done of the operations, you rely on the compiler to do it for you. The second is explicit. This is like type hints, where you define what the sharding should be on the data, but then JAX does the collectives for you. And lastly, you have manual, where you define both the sharding and the collectives. So in the tutorials today, we'll not be doing the manual one because it gets a bit hairy, but it's good to know that you have that. And for torch, I'm not covering torch today, but for torch you have something called torch distributed. So torch distributed has a lot of the same concepts. So you have a device mesh, you have a distributed tensor, and a device mesh, the same thing as JAX arrays and JAX device meshes. And you have the same sort of collectives like all reduce, all gather. And PyTorch distributed supports these 4. Well, you can build more parallelisms using PyTorch distributed, but it's like it gives you examples of these. We'll talk about other parallelisms that are being done now. We'll cover these 2 in our tutorial today: fully sharded data parallel, and tensor parallel. We'll not cover pipeline parallel. But now with LLMs, there's even more types of parallelisms that are being done, and a lot of them are not really supported by default in either PyTorch or JAX. You have special libraries like Megatron from NVIDIA or DeepSpeed that you'll need to train if you were to do anything very new. Okay, so that's the end of our first tutorial. So we saw how you can set up a device mesh, which is a logical arrangement of your TPUs. It could be GPUs. You could arrange them in a 1D array, 2D array, 3D array at max. We saw how we can create sharded matrices and how we distribute them across devices. And lastly, we saw how if your matrices are distributed across devices and you do math mults on them, how you communicate information in order to get the full matrix multiplies. So I'll pause here briefly and I'll take questions because I think there might be questions. Sure.
Could you talk a bit more about the LLM parallelizations that are not supported? Which types are you talking about?
So the latest one I would say is expert parallelism, where you use mixture of experts. Each expert's full network is on one device, but then within the device you can do other sorts of parallelism. The other I would say is like context parallelism. So it's glitching out. Context parallelism is like, say you have a sequence of tokens that now you have to predict the next token. You can split up along this sequence dimension. There's also sequence parallelism, which is different from context parallelism. But yeah, so there's context parallelism. So if you want to do like this, I guess, very new stuff, Torch does have a native library that they have been building, but it's under like very active development. So it's
I just love my time on that.
yeah. So Torch Titan like supports some of these newer. Yeah, they support context parallelism, for example, and they are like actively working on supporting, for example, like a mixture of expert parallelism. Yeah, but I think as a beginner, probably PyTorch distributed is what you would want to start with, because you also have a lot more. Well, Torch Titan is kind of like a collection of recipes for training, versus Torch distributed, which has the like primitives and everything. And in JAX, essentially, yeah, everything you can just do in JAX. But and I won't go into it, but for example, TPUs have some just unique properties compared to GPUs. So for example, like pipeline parallelism is not something you'd care about too much for TPUs, because for GPUs, if you have like more than 256 GPUs together, like there's some bottlenecks that start to come in, and for TPUs those bottlenecks don't come in. Like you could scale to thousands of TPUs and not have to worry about those. These are like bottlenecks that come in from like having just so many nodes and things like that. More questions about sharding and device meshes and matrix multiplies on sharded matrices. If not, we can continue to the second part, data parallelism. So you could go back to the URL mintex.readthedocs.io. And same thing as before, open in Colab and set your runtime to the v28 TPU runtime. Oh shoot, I just realized I only have half an hour. Okay, I'll have to rush through things a bit. Okay, let's start with the data parallel and FSDP part, and if we have more questions about sharding, we can take it at the end of the tutorial. Oh, I've hit usage limits. I've been using it yesterday as well, so I'm not surprised. They have a 24-hour. I can just switch to a different Google account. But you shouldn't. I think around 3 hours per day is what they offer for their free TPU instance. And if you have Kaggle, it's even more. I think it's like 30. I think like for a 30-day period, you get around 90 hours. Oh, that works out to be the same. Kaggle has more TPU accessibility, I would say. The only problem with that is like you don't get terminal access in Kaggle. Okay, so before we start with transformers, let's start with a simple version of a transformer layer which is fully connected. You have the input, which is of size b times data dimension. Then you have the first fully connected layer, the d times this activation dimension. The second one is activation times d, and then the output is the same dimension as the input. This is standard in sequence modeling. So for in language, you take the same dimension of input and get the same dimension of output. So as we scale up training, for example, Llama was trained on 2048 A100 GPUs. If you were to train the smallest Llama model on one A100 GPU, it would take about 166 years. So we need to, as we scale our data, as we scale our model, we need to train on more and more devices. And the ideal goal for scaling would be strong scaling. So strong scaling is when you add more devices, your model training automatically speeds up. But strong scaling is not a given. Like, for example, if you add more devices, you will have to move more data around. And the more data you have to move around, the more communication costs you incur. So, and this is some theory that I don't think I'll have time to cover, but what you would want is that the time spent doing communication is less than the time spent doing the compute. And that way you can arrange your operations in such a way that the communication times get hidden somewhere during the compute times. Okay, let's start with data parallelism. So data parallelism, the name implies we are parallelizing our data. Quite straightforward. So what we do is our input data matrix, we shard it along the batch dimension. And the model is fully replicated on each of the dimensions of the mesh. So what you can do with this is now you can perform the matrix multiplies on each shard of the input and get a sharded output. So during the forward pass, you don't even need to worry about any collectives. This is completely logically consistent, and it can be done by each shard on each of the devices. So this is just a visual image of what data parallelism is about. You're sharding the batch, sharding the first dimension of the data along the batch dimension. So this is what I said, in forward pass, you don't even have to worry about any collectives. You can just perform your operations on each shard of the batch, and the output will be a sharded output. Now in the backward pass, when you are calculating your gradients, you need to get the full representation of the data, because you need to weigh by the full batch when you're doing batch gradient descent. So first you calculate your output loss, then you calculate the sharded version of your loss for the first matrix, and then when you do the update for the weights for this one, you'll need to do an all reduce, get the sharded version of the loss output with respect to the weights from this layer, and get it from all the devices before you do so to get the next iterations weights. But this is not on a critical path. So what that means is we can continue doing the rest of the operations, because this is an update for the weights for the next time step. We can continue doing the rest of the backward pass while we do this async. So we can do it at a time. We can hide the latency of doing this while we continue on with our backward pass. And then the same exact steps are repeated for the second fully connected, well, second in the backward pass. So this matrix, we do the same sharded backward pass, then we do an all reduce, and finally we get uh, the loss with respect to the input, and we need this one for the next iteration. So I'll skip through the compute bound and the communication bound part of it, the math, but what it works out to be is the batch size on any device, so B by X here, should be greater than the maximum throughput of that device, so the number of operations that device can perform. So for example, like for latest GPUs, it's like 2000 teraflops or something, divided by the time it takes to move data from one device to the other, so the bandwidth. So for example, I can't recall exactly how much it is, but it's usually like order of 100 or 1000 times smaller than the compute throughput. So usually you can have batch sizes which are quite reasonable for modern like training setups, and not be bottlenecked by any data movement, because all the data movement that you have is just in the backward pass, and it is very async, so you can hide it while you do the rest of the backward pass. So for example, for the V28 TPU that we are using, it works out that if you have 181 data batch size on each device, you'll not be bottlenecked by data movement. So in the interest of time, I'll skip this. I'll start with, I'm just skipping the data parallel with the JAX part because it's kind of redundant. When you are writing neural networks, you are not writing them using pure JAX. So JAX has an API that is quite similar to the PyTorch NN API called flags.nnx. And we can define, for example, an MLP model that if you look at it, it looks very similar to what you would have in PyTorch. So this is a high-level API, so that's what we'll use for our data parallel training. Okay, so we define our model. It's two linear layers. The first one we pass the output through a ReLU, and then we have the second one. And we define a model size 128 times 2048 times 128, and then we replicate our model states. So the state of the model is essentially the parameters, the gradients, and for the optimizer, the states are things like the momentum values, something that you'd carry on from previous iteration to the next iteration. So we have replicated, which means each device has a full copy of our model, full copy of our optimizer. I need to go back and define some stuff. This is what I need to define. So I'm taking my 8 devices, and there is a sharding that I'm defining called batch sharding, where the first axis of the data is sharded across all of these 8 devices. And the second sharding I'm creating is called a replicated sharding, where nothing is being sharded. So every device will have a full copy of whatever matrix we are sharding using named sharding. Okay, so let's go back down. We create our model, we put our model on the replicated sharding, and you can visualize it here. So linear 1 is the weights of the first linear layer. You'll see that they are copied on all 8 of our devices. Then we define our training step. Pretty straightforward. We do a forward pass through the model. We have a mean squared loss on the output, and then we do the loss and the gradients calculation, and then we just call our optimizer. So very similar to what you might be familiar with in PyTorch. So here I'm creating sort of a contrived data set to visualize sequence modeling. And this is just sort of using trigonometric functions to create a sequence. The blue one is the input sequence, the orange one is the target sequence. And in the next tutorial, we'll do actual language modeling, but this is mathematically the same thing. Like the input has a certain dimension, output has the same exact dimension, and you have steps for which the inputs and outputs are obtained for your data set. Okay, so I've defined a batch size of 8,192. Remember, we want to be more than 181 per device to not be bottlenecked by communication. And let's do our training. It might take a few minutes. And this is how our data is sharded. Now you can see the data is sharded on the batch dimension across the 8 devices that we had. And it might seem a bit counterintuitive why it's like arranged in this way, the devices 0, 1, 2, 3, 6, 7, 4, 5. While it trains, I can give you like a brief explanation, because the way TPUs are arranged together, it's in a toroidal shape. It's not a linear shape, and the reason that is because that way, for example, when we saw all gather or all reduce, where we are sending data in both directions, if you have a toroidal arrangement, you can do it faster versus if you had a linear arrangement or a circular arrangement. So this will train for a few minutes. I'm just gonna skip the training part, and you'll see that once you have you can update your dereplicated neural network and optimizer, and then you saw this would be your training loss, and the green is what your model is predicting now. So we trained it in a data parallel manner, and we are able to get quite close to our target sequence. So I know I rushed through it a bit, but data parallel is sort of straightforward. There's no collectives you need to worry about in the forward pass. You can just do the sharded operations. Only in the backward pass you'll need to do the all gather. Questions on data parallel? While the training runs. Okay, I'll continue. And I'll stay behind after the workshop. You can ask your questions. So with data parallelism, we have solved the size of the data as a bottleneck for our training, but we have done nothing about our model. Like if your model is too big to fit on one device, you just simply cannot use data parallel. You have done nothing to solve the memory pressure from your model. And it involves a lot of duplicated work. So if you think about, we have the full optimizer state, which is duplicated across all devices. We have the full parameters that are duplicated across all devices. And we don't, like this adds up, the memory costs add up. So for example, this is shown here, the baseline in the first row. Like for a certain model parameters, it takes up 120 GB to do the data parallel. If we were to replicate the model, the gradients, the parameters, the optimizer states. So there was this great paper called Zero, stands for Zero Redundancy Optimizer, where they came up with algorithms to shard each one of these, and they benchmarked how it works. So 0, 1 stands for when your optimizer states are sharded. So the momentum, for example. 0, 2, both your optimizer states and gradients are sharded. And 0, 3 is parameters, gradients, and optimizer states are all sharded. So when I say sharded, they are being sharded along the exact same mesh as your data. So the 0, 3 sharding that I'm talking about here, it's also called fully sharded data parallel. And it might be a bit confusing, like data parallel, but what fully sharded means is that your models, parameters, your gradients, and your optimizers are all being sharded. So it's not like your model is not being sharded. It's just that they are being sharded along the first axis corresponding to how the data was sharded. So this is your data, you're sharding it on the batch dimension. This is your model, you're also sharding it on the batch dimension. I'll skip through the algorithm because I think this image is a better. Is the whole thing visible? Or I'll zoom in a bit. So in data parallel, we had our local forward, didn't have to worry about any collective at this point. Did our local backward. For the local backward, we didn't really need to do any collectives. It's just when we do the updates, we need to have collected our weight updates for both the matrices. So we do an all reduce, and then we sync our gradients, we update our weights locally, and then we repeat the same process. This was data parallel. Now in fully sharded data parallel, so model is sharded, optimizer states are sharded, and the gradients are sharded. So we have our model shard. First we do an all gather on the weights so that each copy has a full model. Then we do our local forward, and then we do an all gather on the weights of the next step for n layers, for example. And then we get our backward, same as the previous one, we get a local gradient for this. Then we do a reduce scatter, gather our grads across devices, and then we do the local update, and then we repeat the whole thing. So the nice thing about FSDP is here we had an all reduce for our weight updates. Here we have all gather followed by a reduce scatter. And if you go back to what I talked about in the previous tutorial, you can break down an all reduce into all gather and a reduce scatter. You just have split them up in forward pass versus backward pass instead of having it all in the backward pass. But the nice thing about this is you have not only reduced your memory by sharding your data and model and optimizer states, you haven't really added any time to the algorithm because your all reduce is now broken up into all gathers followed by reduce scatters. So this is why I mentioned the breakdown of the collectives. There's only like added collectives during the forward pass, but they are reduced by the same ratio in the backward pass. So essentially, whenever available, you should just use FSDP all the time. If you are doing data parallel, the only time you wouldn't want to use it is if your model is small enough where you can fit the whole model in one device. So this is just saying the same thing, like the bottleneck ends up being the same as data parallel. Okay, let's walk through quickly an example of FSDP with flags. So we define same mesh as before. I'm calling it FSDP just to differentiate. It's the first axis is split on the 8 devices. And we define our name sharding. So the way we define is like the name weight 0 corresponds to sharding on the first axis. The weight 1 has no sharding. So remember, for the weights, we shard the first dimension the same as the data dimension. The second is not sharded. Bias, since these are just scalars, we don't really need to shard them. And then data is also sharded along the FSDP dimension. So this is sort of the type hint thing that I talked about earlier. When defining your model, you can just give it this named sharding rules that you would want it to be sharded by. So for example, weight 0, as in the first axis, is sharded. We tell that for the first linear layer, the first axis should be sharded. Weight 1 is the second axis should not be sharded. So we just tell it during the model definition while we initialize these kernels. And if it can satisfy these particular ways of sharding the model parameters, it will just work. It will take care of the collectives for you, for example. So bias, no need to shard, it's small enough. And then for the linear, second linear layer, same thing, sharded as before. The next thing we want to do is for our optimizer, we now want to shard our optimizer states. So I have created a function here which wraps on the variable that is used in JAX. And the idea of creating this wrapper is now when we create our shardings here. So for example here, we can force, for example, what the shardings of our optimizer states will be. And we force them to be same as the shardings for the parameters. And then we force, this is the type in that we tell JAX, oh, both the model states and the optimizer states should be sharded this way. And you can see it here. The weights of the first fully connected layer are sharded in the same way as the data was. And the second fully connected layer are sharded same way as the data was. And the momentum state, the optimizer state, is also sharded the same way. I'll just skip through the training part. You can do it. It's the same thing as before. There's no change in the code. What the change in the code was in the model definition and the optimizer definition. And you'll see that it works out. Your model, you could increase the model size a lot. I've trained with the same model size just in the interest of time, but you could get away with a much larger model size in FSDP versus in DP. So I think I'll go back to this image since this was the key image in this tutorial. And I'll take questions before quickly moving on to tensor parallel. I lost track of time. I thought we had until 11:30. Questions here about what's happening in DP versus FSDP? Sure.
So is the maximum amount of parameters loaded in memory at a time just equal to the maximum size of the layer that's gathered for each layer before you move forward?
So when we do the gather, we are not moving the full layer across. Like we are doing it, if we go back to the first one. So what we are doing is like we have multiple layers, right? And when we are doing the gather, we'll do it for one layer. And that doesn't mean that the full model weights are being copied, like everything is being replicated for that like time step. We'll do it for one layer and then we do the forward pass and then we get rid of it. And then we do it for the next layer and then we get rid of it. So at any time, yeah, like when you do, for example, FSDP, you should wait until like the first training step finishes and the maximum memory that at any point your model takes, that's the maximum it will ever take. But it's not the same as the full model size, I would say. Like the maximum layer size, I guess, yeah.
So the maximum memory is the maximum layer size, not
Yeah, the maximum of one layer size plus all the shards, because the other layers will still continue to be on the each device, right? Yeah. I added it as a reference at the end, but I'll just, since we are like so short on time, I'll just open up this great, it's a book / website / tutorial thing from Hugging Face that you can go through, the Ultra Scale Playbook. And there they talk about, for example, yeah, like all the different parallelisms and how to think about like what the largest memory size would be using any of these parallelisms and things like that. It's just called Ultra Scale Playbook. Okay, I'll move on to the third one, tensor parallel, and I'll give you the gist of what tensor parallel is, and then since we have already covered a lot about sharding, I think it will make sense. Okay, so previously we sharded along the data dimension, our model. Now in tensor parallel, we are sharding it along the activation dimension, so the inner dimension of our weights. So the first dimension is being replicated, the second is being sharded. Let's skip through the algorithm. So the example I've shown here, we are doing sort of 2D parallelism. So we are breaking down our 8 devices into a mesh of 2 times 4. The 2 is where we are sharding the data, and the 4 is where we are sharding our activations from the model. Exact same thing as before, the same way we were giving type hints to flags when defining our weights. Now we are telling it that the outer dimension should be sharded along the model dimension. We are not sharding the inner dimension. The data is just being sharded along the data dimension. Skipping ahead. Okay, so this is useful. So now I have sharded it in a way that the linear 1 kernel, the weights of the first linear layer are now sharded across devices, but not in the same dimension as our data was. And the linear 2 is sharded in a way that we can do linear 1 times linear 2 locally without having to worry about collectives. In the forward pass, in the backward pass, we'll worry about collectives. Same exact data set that I used before, this fake data set that I created, and then I train it with 2D parallelism now, where our data is sharded across a dimension of 2. So 4 TPUs have one shard of the data, the other 4 have the other shard, and the model is split up across 4. So groups of 2 TPUs have each shard, and I show that we achieve like good results. Okay, so when we do transformer training with tensor parallelism, for the MLP layers and the attention layers, if you think about it, even the attention layers are essentially just feed-forward layers, and then you do some recomputation on their outputs. So the same way we split up the activations for a fully connected layer, we can split up the activations for our attention layers across whatever model parallelism dimension we have chosen. So this image is from the Megatron LM paper. So Megatron is this package from NVIDIA, and they have a ton of papers on different sorts of parallelisms. So they were the first to introduce the word tensor parallelism and sequence parallelism. So this is how you would shard your model if you had an LLM instead of an MLP. So you'll have the V, Q, K, all of these like sharded along the same named axes that I had for the MLP. So let's do this. Let's see, we have 5 minutes. This is a not nice thing about working with free TPUs/GPUs. Okay, so maybe I'll just skip ahead and look at the model definition. So now what we are doing is the same thing as before. For our multi-head attention, we are giving it this type hint that when you initialize the multi-head attention layer, don't split the first dimension, split the second dimension along the model axis. We are splitting the biases in this case as well. You often don't need to split the biases because they're just scalars, like they don't take up a lot of memory. So the first dimension is our batch dimension, second dimension is our model dimension. And then same thing for the other layers, the linear layers, the second linear layer, the layer norm. And this is our full transformer block. Then we put together a bunch of these. So we put together a bunch of these transformer blocks to create like a mini GPT. And of course, like you can't really train anything very big. So I have 8 blocks, small vocab size, small dimensions. And then I use this data set from HF. It's called the Tiny Stories dataset, which is about like stories, I guess, written for kids. We train the model, and I have the output. You can run this on your own. It will take about an hour to run, and like this is the garbage that it generates without any training. After first time step, it keeps repeating the same word, and then after say 8,000 steps, you'll see it starts to make sense. It looks like an actual story. And this is our training loss, and I know I rushed through it a bit, but the code will be available. This website will be there forever. It's just hosted on Read the Docs, so you can go through it, run it on your own time. The main thing about the model definition was just this, like the sharding hint that you are giving to it. Now you're sharding on the activation dimension, not on the batch dimension. Okay, so one last, since we are, so I have like a one, like what you can read next sort of tutorial at the end. So these are what we covered earlier. So you have data parallelism, where your data is split up on the different devices. Model is replicated fully on devices. You have tensor parallelism. You can have data replicated on all devices. You split up your model activations on each of the devices. Now you can have something called pipeline parallelism. So data and tensor, you can think of them as intra-layer parallelism. So each layer is sharded across devices. Pipeline parallelism is inter-layer parallelism. So you kind of group your model into stages, and each stage is just a group of layers, and they are sharded on different devices. So in order to do the forward pass, you'll do it in this sequential manner. So like the first stage, second stage, third stage, so on, and then you do the backward pass. So in pipeline parallelism, this is called a bubble. This is a lot of time that is being wasted not doing anything. So you split it up into micro batches. So you do the forward pass from the first stage on a micro batch. Then once this is done, you can do it the second on this while you do the micro batch for the second micro batch, and so on. So this is pipeline parallelism. Sequence parallelism, I'm gonna skip. It's not as common anymore, not used much. Context parallelism, I think I mentioned earlier. So you have your input sequence of tokens. You split it along the sequence dimension, except that it doesn't. So sequence parallelism had this limitation where it would work in conjugation with tensor parallelism. That's how it was introduced, that's how it was used. Context parallelism, it just works without tensor parallelism. Of course you could mix it. So the first like half of your sequences you can split on one device, the second half on the other device. And then we have expert parallelism. To be quite honest, I don't know much about expert parallelism, but essentially you have groups of 8 to 16 neural networks that make up a large neural network. At any point during inference, for example, only one is activated. You can split them across devices. And then these are the references. I think I already talked about the ultra-scale playbook. This is great. And it uses a library called Nanotron that Hugging Face has. This is a great library. They implement, it's like very easy to understand, and they implement the 3 parallelisms that we talked about today. FSDP, tensor, and I believe pipeline. So you can read through Nanotron, great resource. Then one book I really like is How to Scale Your Model. You can read through this. Then yeah, I think we are out of time, so I'll stop here. Thank you everyone for coming and listening, and I'll take questions async because I think the next workshop needs to start. Thank you.